Hey everyone. So today we're going to be talking about zero shot and few shot learning in NLP, which is an area that's been getting an increased amount of attention lately, and may potentially come in useful for some of you guys. First, I'll say that there was also an announcement about the schedule of our presentations. We may be adding a few things to that, but that's kind of the general schedule. And fortunately, because a lot of you guys are actually working in groups with other people in the course, it looks like we'll have a lot of time to get feedback, which I think is going to be really useful for you guys. So, if you're in a time where you're able to make it, please try to attend the next couple of weeks live so that we can all kind of give each other feedback and support each other with the projects. Sorry, I accidentally muted myself. So first I want to talk about what is meant by few shot learning or zero shot learning, and then we'll talk about how to do that in practice. Okay. So in this class, we've mostly been discussing how you would take a pre-trained model and fine tune it to a task that you want to do. And in order to do that fine tuning, you give the model labeled examples, right? Because that's how models in deep learning learn from being trained on seeing data. And in most of the contexts we've seen, this is data kind of that you would create for your project. You'd have human annotators essentially tell the model what you want it to learn. And we've really seen the power of pre-training in NLP. If you start, from scratch, like Facebook AI research is pre-training Roberta on over 1,000 GPUs and 160 gigs of text. And, fortunately, we are not starting from scratch, but you still may have to produce quite a few labels. And that, that can be costly. And kind of more generally, we've seen that NLP is a very benchmark focused field. And so there's benchmark data sets, which are associated with benchmark competitions, and kind of models get evaluated based on how they do on those benchmarks. And by definition, with these benchmark data sets, you have the data set to fine tune the model on. So we saw last class the example of Squad, the Stanford question answering data set. And that data set has over 100,000 question answer pairs for fine tuning a model. And we saw about how when you fine tune like BERT or Albert or whatever your kind of model of choices on Squad, you can even beat human performance. But a model fine-tuned on Squad may not do so well on another question answering data set. Or we have a quote here from a model that we saw briefly, GPT-3, which remember was the enormous model with hundreds of billions of parameters. It says, to achieve strong performance on a desired task typically requires fine-tuning on a data set of thousands to hundreds of thousands of examples specific to that task. Removing this limitation would be desirable. How much data you're going to have to fine-tune on is going to kind of depend on how different your task is from whatever the model's already been pre-trained on. Okay. And so some of these reasons include if you're doing a task that doesn't really look like the benchmark, you're going to need to put together labeled data to get comparable results. And, especially if you're in kind of, let's say, a low resource language setting, for example, that might be challenging, or just in general, it is kind of a lot of work to put together labeled data. We saw last class how models fine-tuned on one large data set for one task may generalize poorly on another task, even if it's like the same task, but with a different kind of benchmark data set. Because the model has been fine-tuned to be very specific to one particular training distribution. And so sort of the broader goal that people talk about is like artificial general intelligence, which we're definitely not close to. But that you could achieve a model that's able to like learn things in a more human way. Humans do not necessarily require large supervised amounts of data to learn different language tasks. So researchers have started to care more and more about what's called zero-shot or one-shot or few-shot NLP methods and models. Think about this as kind of learning in a more unsupervised way, which is kind of like sort of the direction the field is going. Because we've seen that like when you have labeled data and you have enough labeled data, you can kind of fine-tune the model to have very good performance, even better than human performance. You can still maybe trip it up, but it works. Essentially the supervised problems, like on the benchmarks that the field uses, the models are doing really well. And so sort of the next kind of direction to go is to ask, is there a way where we can get models to work without having to have so much labeled data? And one branch of this is like data augmentation, where you have a way to kind of generate your own labels. And another sort of related branch is thinking about zero-shot or few-shot methods, where you're able to have a model where you don't need to train it on much or any data to get it to work on a new task. And so the exact definition of few-shot learning changes with the context, but in general, it applies to a context where you can have a deep learning model that only requires, a relatively few labeled examples to achieve satisfactory performance on some novel tasks. So you're not needing like thousands of labels, like a relatively few number of labels will do the trick. One-shot learning, as you might guess, is like few-shot learning, where literally you need just one labeled example. And zero-shot learning is where you don't need to give the model any labeled examples to perform well on a novel task of interest. And so, for example, if you wanted to do zero-shot learning in the context of text classification, that would imply that you have a model that can learn some arbitrary task-specific classes for arbitrary text without any task-specific supervised training or fine-tuning. And more broadly, you can think of few-shot learning or one-shot learning or zero-shot learning as getting a model to do something that it wasn't explicitly trained to do, or getting a model to perform some previously unencountered downstream task without having to alter its parameters. So this is kind of the opposite of benchmark chasing, where you have some benchmark task and your goal is to fine tune that model on thousands or tens of thousands or even hundreds of thousands of labeled examples for that task. But obviously this is kind of a challenging thing, and hence the reason why, deep learning is still dominated by kind of supervised fine tuning, because it's obviously difficult to get a model to do something that it wasn't explicitly trained to do. And, so like at its core, like a lot of the kind of methods for few-shot learning go back to transfer learning. Like if you can train a model in the first place on, a diverse amount of data, so it's just good at doing a lot of stuff, there's a higher chance that it will transfer to what you want to do with relatively few or even no labeled data. And so, we've talked about earlier in the class how really the trend in the NLP literature is that if you want to do a better job, train a bigger model for more time on more data. And you could take this paradigm to few shot learning or zero shot learning. And so, the example of this is OpenAI's GPT-3 model. And like literally the title of their paper about it is Language Models Are Few Shot Learners. And so what they did was to train this enormous model. Remember, it's like a stack of 92 transformer decoder blocks. So it's like a generative model. And it has 175 billion parameters. And it is trained on a 300 billion token corpus. So they just trained it on this massive amount of data. And the argument is that it can do, a reasonable job on downstream tasks without having been explicitly trained or fine-tuned to perform well on them, just by virtue of the fact that it was pre-trained and exposed to like such a massive amount of data during the pre-training. And it's like a decoder model, right? So it's just pre-trained by making it like predict the next word. And so the punchline is the paper is that, you're just using the transformers decoder architecture, and the knowledge acquired through lots of language modeling can be transferred very effectively to non-language modeling tasks. And sort of the idea is that with more and more parameters, you can do better and better at this, and maybe be at least kind of somewhat competitive with the state of the art, with relatively few labeled data points, because the model's just gotten so much from being pre-trained on such a massive amount of data. And so you see this is like a graph from the paper and looking at models of different sizes. So the 175 billion parameters is the GPT-3 kind of full-size model. And it's doing, benchmark tasks with 0 shot, 1 shot, or relatively kind of few shot learning. And you can see like, yeah, like with 0 shot learning is still doing pretty horrible, like 10% accuracy. But like, if you look at the smaller models, they're essentially at 0% accuracy. So kind of like, at least it's doing better. And when you get into the realm of kind of few shot learning, again, it's not doing like that great, but it's, kind of up to like above 60% accuracy. And that's still kind of way better than you do with few shot learning with a model that has way fewer parameters. Okay, so as was kind of clear from that graph, it's still not going to generally achieve state-of-the-art performance compared to models that were fine-tuned on task-specific data sets and that are still going to like tend to be the best performers. So this is probably not like, the solution around needing labeled data. But so you kind of benefit by not needing to assemble this large task-specific data set, but usually you're not going to get the performance that you would get if you did that. And so you have to kind of keep in mind, what's sufficient performance. And I'd say with like, with GPT-3 and OpenAI, they have this kind of like partnership with Microsoft. And I think it's like pretty geared towards kind of like commercial applications. So let's say for some reason you have to call customer service at Amazon. It's probably not that great of an experience, but you kind of like have to deal with that. And, like the goal with the language model is you could have some kind of chatbot that you called instead, and it's still not really quite at a level where it's being used for that performance. But I think the goal would be to kind of like, get to that level of performance, which is kind of, different than what we might need for like, a paper like that we're writing, where we really want to have a pretty high performance. But there's some other approaches as well. And so the sole paradigm isn't just to get a bigger and bigger model and then use it off the shelf. And so we'll also talk now about some of the other approaches. And I think there's always a chance that even if this wouldn't be the approach you'd use for the kind of final results in your job market paper, doing something zero shot or few shot may give you a sense of whether something's likely to be interesting before you kind of invest all of that time in putting together lots of labeled data. So it can be, potentially useful in that sense, even if the accuracy isn't really what it would be with your, 2000 example labeled data set. Okay. And so, yeah, you're probably not going to actually use GPT-3. Maybe it will be unrolled on Azure and you can use it there. But there's other alternatives to zero shot learning. And so kind of one of the best resources for doing few shot learning in practice comes from a blog post written by Hugging Face. And this is just kind of a more general phenomenon that in terms of kind of new NLP research, it's becoming increasingly dominated by Hugging Face, which is kind of interesting that this kind of NLP startup is actually doing a lot of the interesting research work in NLP. And in particular, he frames classification as a natural language inference problem. And I think that this framework is really useful. And so the idea behind framing text classification as natural language inference is to use a pre-trained natural language inference sequence pair classifier as a zero shot text classifier that you can just use kind of out of the box. And so natural language inference is a task that takes as input a premise and a hypothesis sentence, and it performs three-way classification as to whether the given premise entails, contradicts, or is neutral with respect to the hypothesis. And this has been kind of another central benchmark task in NLP. And so there's a bunch of natural language inference data sets that models have been kind of fine-tuned to and evaluated on. But the idea is that if one takes an arbitrary piece of text to be a premise and takes a sentence declaring that text as a certain topic to be a hypothesis, the natural language inferent entailment would correspond to that piece of text being declared a certain topic, as you would in a topic classification problem. So if you have a headline about, Kansas City Chiefs won on Thursday night, and that was your hypothesis, and then you have a premise this article is about sports, then rather than doing a topic classifier where you're taking that headline and you have a classifier on top of it to say, is it this sports or news or the weather, you could have that hypothesis sentence, this article is about sports, and treat this as a natural language inference problem. And if you have a model for doing natural language inference that's been pre-trained on just a massive amount of text, the idea is that that might be able to do pretty well out of the box on classification. And so if you go to the Hugging Face blog post that's mentioned, you can see that it's actually pretty straightforward to code this all up with the Hugging Face Transformers API. And there's also a live demo of the classifier which could allow you to just pretty quickly test it out on your use case. And so that's in this link. It's also worth noting that the way that the declaration of a topic is made could have an effect on your results. And so in the original paper that proposes doing this, they show you kind of the templates that they use to create these hypotheses, sentences for classification. And so in some sense, this is just an example of transfer learning that facilitates zero-shot learning. If you kind of structurally, if you're clever in the way you structure text inputs, you can take that information that the model has learned from pre-training and from fine-tuning on the natural language inference data sets and do topic classification, potentially without specifically fine-tuning a classifier. And again, kind of how well this is going to work probably depends on, whether what you're trying to classify resembles what the model was pre-trained or fine-tuned on, because it's not going to have been able to learn something that doesn't look like what it's been exposed to. And so the default zero-shot text classifier at Hugging Face uses a model by Facebook AI research called BART that was fine-tuned on the main natural language inference benchmark data set, which I think we may have talked about briefly at one point in the course. And so just a quick note on BART, because it's we didn't actually go over it before, but it's related to other language models we've seen. And so BART closely resembles the original transformer architecture in that it has both an encoder and a decoder stack. And it frames language model pre-training as a sequence-to-sequence task, like the original transformer. And so BART is trained by corrupting text with an arbitrary noising function on the encoder side, and then learning a model to reconstruct the original text on the decoder side. And so in practice, they find that noising sentences by randomly shuffling sentence order and replacing spans of text with mask tokens can lead to good performance on some tasks. And one of those tasks that it does really well on is natural language inference. And so this contrasts to BERT, where you just replace a certain percentage of the tokens with mask. And so I think, they built the zero-shot classifier on top of BART, both because Facebook AI research has good code and makes it available, and because BART was doing pretty well on NLP tasks, including natural language inference. And so it was, a good choice to, underlie, it was a good choice of a, fine-tuned model for natural language inference. But in principle, you could do the same thing with different models that may have been pre-trained on data that look more like whatever your task is. And so there's a couple of examples of this. And so probably one of the best known ones is this TLDR story. And during the election, they had a pretty interesting classifier to classify headlines as hyperpartisan or not using this framework. And I think they may have taken it down, but you may find a cached version of that somewhere. And it's not perfect, but it does pretty well for zero-shot learning. The blog post author notes that it doesn't really make the model any better to fine tune it on a few examples. So yeah, I think that just like if you're interested in this, go to the demo and like, check it out on a few things that would be of interest to you and see if it's like, if it does a decent job or if it's doing kind of really poorly in your domain. Okay, so that's one approach, which is to treat things like to treat zero-shot classification like natural language inference. Another approach that's also pretty recent is based on a recent paper and what they call pattern exploration training, or PET. And the basic idea is that if you have enough unlabeled training data for your use case, you can create a high performance text classifier by training it on soft labels, which are labels that you predict from your unlabeled data. And so this might be really useful, like, even if the labels aren't perfect, maybe you have a way to create these kind of soft predicted labels for a very large data set. And you can kind of fine tune on that. And then if you need to, maybe fine tune with like few shot learning on kind of a much smaller, high quality labeled data set. And so in order to get these soft labels, what the paper does is to dress up the text in a close pattern, which is similar to language model pre-training. And you have a neural language model guess a completion to the closed pattern that corresponds to a label of interest. And so, for example, like, apples are the color, and then you mask that out. And here, mask might be filled in as red with high probability. And so that would be kind of a high probability label for this task. And the closed pattern would simply be, input, which is apples are the color, mask. And you can train that close by masking information in your data. So it has kind of a lot in common with how language models are pre-trained to start with. And so the idea is to manually create several of these closed patterns. And for each, assuming we have or can make a few ground truth labeled examples, we fine tune a language model for filling and mask. And we can then have all of those closed patterns fine tune models vote on the best fill and label for the full universe of unlabeled training data we have access to, and then consider these to be soft labels for training a text classifier in a supervised fashion. And so this method assumes you have lots of data for unsupervised training before few shot labeled inference can begin. And so in the original paper, they give the following example. So they take this news classification data set. We're given a headline A and text body B. News needs to be classified as belonging to either world, sports, business, or science tech. And then, they make up kind of a few examples and then use that to get soft labels, for this much larger data set of headlines and articles, and then use that as, a traditional data set for fine tuning, but they didn't actually go through and label kind of all those headlines themselves. They essentially, created a few of these closed sentences with examples that they had and used that to predict these soft labels, and then fine tuned on the soft labels. And then you can kind of, after you do that fine tuning on the soft labels, then you fine tune on a much smaller labeled data set. And I think like there's lots of ways that you could kind of apply like a general similar intuition, like, so suppose you were trying to make it kind of like a hyper partisan news classifier. You might assume, that every headline from a news source that we know tends to be really hyperpartisan is hyperpartisan. And you could find, and and not hyperpartisan for something that's like a much more, generally thought to be much more objective, or same thing for right wing, left wing, and the labels aren't perfect. But you take those, you fine tune on that, and that gets you kind of like part of the way there. And then you go the final mile on fine tuning, a very careful hand constructed data set. And you do the final fine tuning with that. So I think this is part of like a more general kind of important thing to think about, which is there a way to get kind of decent soft labels through prediction, and so that you can have this really large label data set that's of like decent quality, and then focus your energies like on a much smaller high quality data set to do the final fine tuning. So like the basic idea is that they're trying to find the way to extract knowledge buried within a pre-trained language model to generate text classification. Okay, and so we've talked about few shot and zero shot methods, and I know this has been, it's the literature is a bit thin, and these are like both kind of really recent papers, but this is kind of an exciting area to watch, because I think you're going to see a lot more research on this coming up in the coming years, just because we are getting to the point where like these models work really well with your kind of large benchmark data sets. And this is the next general question, like how can we train these with less intensive human labor to create the labeled data. But another paper that I wanted to flag is called TANDA, Transfer and Adapt Pre-trained Transformer Models for Answer Sentence Selection. And so in this paper, they say we first transfer a pre-trained model into a model for a general task by fine-tuning it with a large and high-quality data set. And then we perform a second fine-tuning step to adapt the transfer model to the target domain. And they find that you can do this to get state-of-the-art performance on many different tasks, which is essentially like, what I was just talking about. So that large data set, could be something that you predict with soft labels like we just saw, or it could be a data set that's like related but not kind of exactly what you want to do. But the point is you're going to be able to learn something from that large data set that takes you closer to kind of where you want to go. And so, back when we were talking about like document layout analysis, we mentioned like, oh, well, you may want to start out, initialize your weights to the PubLayNet weights, which is like a large data set that consists of modern scientific articles. And the authors were able to very cheaply create this large labeled data set because the layout information is there embedded in the PDF. And so you have this data set with hundreds and hundreds of thousands of objects. It doesn't really look like the historical table that you want to digitize, but they are documents. And so it's, closer in a sense than the MassCar CNN just pre-trained on ImageNet. So you initialize with that, and then you fine tune to the labels that for your specific documents that you've carefully created. And that will potentially allow you to have to create fewer labels. And so I think that like you always, just because deep learning is so data hungry, you always want to be thinking about, is there some large data set out there that I can use with relatively limited cost that's like relevant to my application, whether that's with, text, like predicting soft labels, whether it's, using a data set that another researcher has put together to fine tune first, and then fine tuning again on your own data set. Kind of anytime that there's information out there that you can like learn from, that's going to get you closer to the few shot learning paradigm. Okay. And so, again, that like there's kind of like a fine line between like, well, what would we just call transfer learning and what's essentially few shot learning. But again, kind of, at its core, few shot learning is basically transfer learning, because you're trying to get that relevant information kind of out of the model that's been essentially pre-trained on something else. And, so in terms of, how useful this is likely to be to you, again, I think it's going to really depend on the application and what you're trying to use it for. And so I think it always makes sense when you want to do a project to try to figure out with the minimum amount of work if the project is likely to work out, because most ideas don't. And the quicker that you can figure that out, the better. And so I think, that it's worth being familiar with this, especially like the Hugging Face zero shot text classifier, which, it may not be applicable to your problem, but it's kind of one of the best known examples out there of sort of an implementation for zero shot learning. So it's worth being familiar, and you can check it out and see if it kind of gives you anything that's, useful for what your text is. Even if you see, well, this is not like, something that I would use in an ultimate paper, it may allow you to really cheaply get a sense of like what your data look like, or whether something is likely to pan out. Like Hugging Face makes it just really straightforward to implement NLP code. There's also examples that go kind of beyond text classification. And so OpenAI has a model called CLIP that does zero shot classification for image and text problems. And so there's also some zero shot methods in other fields. I mean, unfortunately, like you're not going to have a complicated table that you can learn its layout through zero shot learning or whatever, at least kind of based on current technology. But, it's a growing field, and it's worth paying attention to. And I think it is worth checking out the Hugging Face library to see if you're doing kind of text classification stuff, to see how far that you can get with that. So are there any questions at all on any of this, or how it might apply to your projects or other things that you guys are interested in? Okay, so next class, we had listed on the syllabus that we were going to do some stuff on summarization, but I'm not sure how really useful that would be. And so instead, what we're going to do is kind of circle back and talk a little bit about a new and pretty exciting literature on visual transformers, which tries to take a transformer type architecture and apply it to vision problems, which is pretty cool, because we've seen how it's completely transformed NLP, and this is still like a pretty active area of research, but I think you'll see kind of vision transformer applications take off a lot over the next few years. And so we'll have kind of a bit of an introduction to that. And then again, we'll have the class presentations. And as I said at the beginning of class, because a lot of you guys are actually working in groups, this is all the better because it gives lots of time for feedback. And so I know that Zoom is sometimes like a difficult environment for it, but please, as long as you're in a time zone where you can kind of try to show up live for the presentations. And I'm sure that your classmates would all really enjoy getting as much feedback as possible on their projects. And so we're all really looking forward to that. All right. Thank you, guys.